Bienvenidos, welcome everybody. Can you hear me? We are very pleased to have Ellen Howell. Dr. Howell got her PhD from the University of Arizona in 1995. She did a postdoc at the University of Puerto Rico at Mayagüez. And then since 1999, she has been staff astronomer at the Arecibo Observatory. And so today she's going to tell us about what do we learn from radar observations of asteroids and comets. Dr. Howell.
There. It's on. Thank you very much for having me here. I'm very pleased to be able to visit this beautiful place. Have an excuse to come learn more about what you do here. I'd like to tell you a little bit about the kinds of observations that we do of comets and asteroids at Arecibo. The planetary science is only a small part of what is done at Arecibo Observatory, but it's an important part, and so I'd like to tell you more about it. First of all, why do we study asteroids at all? There are mainly three reasons. The first is that, whoops, that's not what I wanted to do. That asteroids are relatively unprocessed, and so we look at asteroids to learn more about the early formation of the solar system. And we also are interested in asteroids because, especially the ones that come close to the Earth, because they are a source of raw materials in space. And as we move towards doing more things in space, we're going to need a source of raw materials, not so much metals and mineral resources, but water. Near-Earth asteroids are probably the most accessible source of water in space. And the other reason is the impact hazard. Although it's not a very likely event, the consequences are large. And so we could, and it's one of the few natural disasters that we could actually know about ahead of time if we look for all of the asteroids large enough to cause us a big problem and see where they are and see if they are going to impact the Earth in the next 50 to 100 years. So that's another reason for learning more about near-Earth asteroids. So a quick inventory of the solar system. Aside from the sun and the planets, however you want to define those, there are a lot of small bodies. There's a lot of other things that are orbiting the sun. And as of last night, we have over 400,000 minor planets or asteroids. And while most of them are in the main asteroid belt between Mars and Jupiter, plenty of them stray out beyond that zone, and many of them come close to the Earth and even closer to the sun than that. 190,000 of those, I would drive this very well, are numbered, and all that means is that the orbits are well enough known that we can predict for 5 or 10 years with very good accuracy where that asteroid is going to be and not confuse it with another object. The unnumbered objects still have good orbits for a fairly short period of time, and then if they're observed again, the orbits become much better. We have comets. The numbered comets are the periodic comets that we know are coming back. There's also a good number of long-period comets where we see them once, and they won't come back for 10,000 years or more, and so someone may see them, but it's not us. Oh, and a lot of the minor bodies now, both in the main belt and among the near-Earth asteroids, we know many of these asteroids have satellites, and this is a fairly recent discovery, and radar plays a very big role in understanding these objects, and I'll talk more about that later. So, as I mentioned, most of the asteroids, this is a view looking down on the solar system. The planets are shown on their orbits, but not, of course, to scale. So here's the orbit of the Earth, and here's Mars, and the asteroid belt is mostly here between Mars and Jupiter. although there are asteroids that are co-orbital with Jupiter. And there are a lot of asteroids that get perturbed out of the main belt that cross into the planetary zone in here, and the ones that come within 1.3 AU of the Sun are known as near-Earth asteroids. And those are the ones that I'll mainly be talking about today, because those are the ones that we can observe well with radar at Arecibo. So radar astronomy is one of the few active experiments in astronomy. We actually send the light out and then look at the return signal. And as the radar bounces off of a solid object, we can learn a lot about that object because we know exactly the characteristics of the light that we send. We send a circularly polarized monochromatic signal out, and then we receive over a broadband or a broader wavelength, so we see the light Doppler shifted both towards and away from us if the object is rotating. And we also look in both polarizations so that if the object is smooth and we get simply a mirror reflection, we would expect the polarization to be in the opposite sense as the light that we send. If there are rough parts on the surface or multiple bounces, then we can get some of the light in the same polarization as what we send. So we receive in both. And that tells us something about the scattering properties of the object. So let me explain a little bit about how a radar image works, because it's not intuitive, and even after looking at these things for years, you can get fooled as to what it actually, the coordinate system is a little bit hard to understand. So I'm going to go through it quickly here, and then I'm going to show you a little movie that will help you link what the radar image looks like for what you would see in the sky, and I think that'll help give you a better feel for it. So if we consider a simple spherical object shown over here that's rotating so that this part is coming towards you and this part is going away, then as the light hits it, the first received signal is coming from the closest point to you here in the center, and then in the next time step you're seeing light reflecting from a ring a little farther back, and then a little farther back than that, and etc. So this first part is here at the top of the image, and this next ring is coming from a little bit farther back here, and then this outer ring is coming from as far back in the image as you can see. So as the object rotates, the distance from the observer is from top to bottom in this image. The other axis is the rotation of the asteroid. So the part that's coming towards you is Doppler shifted to one side, and the part that's going away from you is Doppler shifted to the other side. And if it's a rigid rotator, then that maps into a spatially resolved image. But this pixel here and this pixel here have the same range and the same Doppler shift. So the light coming from both of those parts of the asteroid map into the same pixel in this image. So you can't tell which hemisphere a particular feature is really coming from. Okay, let's just... So one important piece of information that we get from radar images is that we get a spatially resolved image of the target. We get a direct measurement of how big the asteroid is. It doesn't depend on thermal models. It doesn't depend on any other kinds of interpretation. It's simply the speed of light. And so it's a very direct measurement. And the depth in range of the asteroid is a good measure of its radius. And even for irregular objects, this turns out to be a fairly robust measurement if you average over the different viewing geometries for a given asteroid. Now, this is a little movie put together of KW4, which was a near-Earth asteroid that was very well imaged fairly recently. And it happens to be a binary. It has a satellite. And so if you were sitting out in space in your little spaceship, this is what you would see. You would see the asteroid here and its satellite moving around it. And over on this side is the corresponding radar image. So the primary asteroid looks like it's rotating around this way as you see the radar coming off of the rotating body here. And it's a fairly rapid rotator. It rotates in about 2 hours, 2.5 hours or so. And so the Doppler spread, which is the extent in this direction, is fairly large. Now, the satellite, see the satellite disappears for a short time and comes out of eclipse, is shown here. And so when it's at the same distance from you as the primary, like right there, it's nearly on top of the image, and now it's here in front, and it's coming up closer to the observer. Remember, the observer's up here at the top. And then as it orbits back around, it shifts in Doppler shift to be moving away from us, and then goes behind the primary. And because in this case the secondary is synchronously locked in orbit, so its orbital rotation rate is the same as its orbital speed, which is much less than the rotation rate of the primary. So the Doppler spread is a lot less, so you get a much narrower image for the secondary, which makes it brighter. So in radar images, the secondary tends to be brighter than the primary. Now, we can change the Doppler width of the image. You can process the image at higher or lower resolution to change that. But you don't tend to miss the secondary because it ends up being narrower and brighter than the primary asteroid. So radar detection of binary asteroids is very efficient. Common, but not absolutely universal. We know of several systems where the secondary rotates not in a synchronous orbit, but most of them seem to be. Mm-hmm. This one was. Okay, so when we think about asteroid images, we don't have to imagine what they look like anymore. We can look at spacecraft images, and this is Arecibo showing the very detailed surface properties that were seen from the Japanese Musashi spacecraft, the Hayabusa mission. But radar images from the ground have, these are at similar resolution, 10 meters or so per pixel, and we can get spatially resolved images from radar. Although you might say, well, but if you have a spacecraft image, then we don't need to be doing radar anymore. But there are a lot of these objects out there, and we're not going to be able to send spacecraft to even a representative fraction of them. So if we compare sort of what kinds of things do we learn from ground-based versus spacecraft observations, from the ground, we can get images of something like 25 asteroids per year, whereas we've visited 2 near-Earth asteroids now, and possibly we'll have a few more in the next few years, but we're certainly not going to have hundreds of them anytime soon. And from the ground, we can get this dual polarization, whereas even if you put a radar detector, a radar instrument on a spacecraft, you have to transmit in one polarization and receive in the other, and so you can't get dual polarization from a spacecraft normally. We get something like 10-meter resolution as long as the object comes within about 0.08 AU from the Earth. That's about 40 times the distance to the Moon. And the image resolution from a spacecraft can be better than that, but is often on the same scale for a flyby. But the only way that we're going to get an overall picture of the population at any reasonable cost is to continue doing ground-based observations, because we could build and operate Arecibo Observatory for 40 years for the cost of a single spacecraft mission. So, what is it that we actually measure? We measure the object's velocity dispersion. As I showed you, you see the rotational velocity in frequency. And you measure its range depth, its extent in your line of sight. So we get the size and the shape and the spin characteristics from that. And I've showed this image a couple of times. So this is turned on its side from some of these other ones. But here's the range direction showing the spatial extent in your line of sight. And this is the Doppler extent showing the rotation of the object. So we also measure its orbital speed and its orbital position. And usually that's known at least approximately ahead of time. And so we use the telescope and the detector to compensate for that and to keep the image fixed in the observer's frame. But as a consequence of doing a radar observation of an asteroid, we always get an orbital improvement just as a matter of course. It's not a separate part of the experiment. And we also measure its scattering properties. We get some information about the polarization, which can tell us about the roughness at centimeter to meter scales. I should mention the wavelength of the planetary radar that we mostly use for this work is 12.6 centimeters, or 2380 megahertz. We have another radar that's the 70 centimeter radar that has been used. It's mainly used for atmospheric work, but it could also be used for very close asteroids. Because with the 12 centimeter radar, it takes us a little less than 4 seconds to switch from transmit to receive. And the round trip time to the moon is about 2 seconds. So anything that's closer than about twice the distance to the moon, we can't image just with Arecibo alone. If objects do come closer than that, then we have to transmit from Arecibo and receive from somewhere else, either the Goldstone dish in California or the Green Bank telescope in West Virginia, or occasionally other telescopes around. Now, the scattering properties are frequently interpreted as telling us about the asteroid material and telling us about the porosity and the density and things like that. But you have to remember that a lot of those interpretations were developed for planetary surfaces, which assume uniform half-space kinds of properties. And a lot of those assumptions are violated for small objects. But we use them anyway, and we get some idea of the nature of the asteroids from their scattering properties. So here's an example of, this is a main belt asteroid that's 200 kilometers long, asteroid 216 Cleopatra, and this is a shape model that was derived from radar observations. It's a very unusual shaped object. It looks like a dog bone, but and the color coding is the local gravity of the surface. But we sometimes find even the very large asteroids are very different in appearance than we might have expected, and the theoreticians are busy trying to figure out how you could possibly get a large metallic object of a shape like this. And they've come up with some ideas, but I don't think there's general agreement yet. That was the local slope for the gravity. So what do we get? Aside from pretty pictures of asteroids, what can we infer from that? We measure the shape and the spin, but that gives us information on the internal structure. If we have, for example, a spherical object, most of these are much too small to be spherical just from self-gravity overcoming the strength of the rock. But we find a surprising number of very small spherical objects. So they must be completely strengthless, just gravel piles. And that was not something that we expected. We also find slowly rotating bars that are asteroids that are extended, elongated. We also find fast rotating bars. And so you can say, well, all asteroids must be these strengthless rubble piles because they've undergone collisions, and collisions will break them up. But it doesn't break all of them up, because we do also find fast-rotating bars that do have to have some kind of internal strength and can have no loose material on the surface. We find irregular objects that we would expect from collisional fragments. And initially, we sort of thought all of these little objects must be these irregular potato-shaped kind of things. But that turns out not to be the case. And it's telling us a lot about the processes that these objects undergo, and trying to think of how they got the way they are. So the overall physical structure of NEAs, understanding the physical structure, is important for all of those general reasons that we're interested in studying them. For understanding how meteorites get delivered to the Earth. Meteorites can be studied in the laboratory in great detail, and most of our ideas of solar system formation and nebular condensation come from the studies of meteorites. But with very few exceptions, we don't know where any specific meteorite came from in the asteroid belt. We don't know its geologic context. And so we'd like to understand better how asteroids get from the main belt to be perturbed into Earth-crossing orbits and then fall on the Earth occasionally as meteorites. And, of course, space resources I mentioned. And if we were to find an object on a collision course to the Earth, we would like to know something about its internal structure in order to know how it is we should best push on it to push it out of the way. And so understanding something about the internal structure of asteroids is relevant to all of these things. And we see all kinds of asteroids. We see all of these kinds of shapes in roughly equal numbers. And so understanding the overall population, we are still discovering new things, too. And so ground-based observations to sample the population is still a very important thing to be doing. So we have some ideas of the categorizations now. We've looked at about 200 near-Earth objects with radar over the last 10 years or so. And we can roughly put them into categories, and we see roughly equal numbers of these. And I'm going to show you some images just to give you an idea of the kinds of objects that we see. So irregular bodies, the thing that most of us probably had in our heads before we had any data, we expected kind of these irregular cratered bodies like this one. And we should see, what happened to my cursor? There it is. We see bumps and certainly crater-like features here and there. And the spin rates should also tell us something about the collisional processes and how these got to be there. This particular one is spinning very slowly. It has a rotation rate of about a week. And it's actually tumbling. It's not spinning around its principal axis of rotation. And the dynamics of that are still being investigated. But we think that initially we thought the spin orientations and the spin rates of these things should also tell us something about the parent bodies that they came from. But it turns out that radiation forces can alter the spin on fairly short timescales for objects near the Earth. And so, in fact, the spin rates are telling us a lot about their evolution, but not very much about the parent bodies that they came from. So we also see a lot of objects that look like they're two lobes, two objects kind of stuck together or elongated. And this is an example of that. This is a series of images, oh, there it is, that you read across like a book. So these are images taken about every 10 minutes, here and here and here. And you can see how there's an overall rotation in this direction of the body. And we see both fast rotating objects like this and slow rotating objects like this. And here's another one, 2001 KZ66, which was rotating in about 4 hours. And so this is about an hour and a half's worth of data, maybe about 2 hours worth, actually. And you can be fooled if you don't have very much information. Just a quick snapshot doesn't really help sometimes, or can be misleading. If you only saw this image down here, you might think, well, maybe this is a separated object. But up here, clearly it's joined together and there's no gap between the two. Okay, and here's an example of some spheroids. A lot of times you can get the rotation rate of an asteroid by looking at the change of the light as it rotates. But if it's perfectly round, it doesn't change its brightness as it goes around. And so if you don't see any change with rotation, it can either mean that it's a slow rotator or a fast rotator or a round object. So the radar image will often tell you clearly which of those you have. And you can see on this one, whoops. Oh, I see. I'm pushing the wrong button here. No. How do I get... previous. No. Oh, help. Here. Just go. I can do it there. Okay. All right. I have to be careful how I push this thing. So in this collage, like before, these are images about every 10 or 15 minutes going from top to bottom, and you can see there are slight changes in the overall shape, but that more or less it's a spherical body that looks the same pretty much all the time. And we see both fast and slow rotators like this. So making a fast rotating rubble pile spherical is maybe something you can picture, but a slow rotating sphere is a little harder to understand. And I don't think we have a very clear understanding of all of the details of this yet. Now, this is a movie of 2006 AM4. This is an object that's 150 meters long and rotates in a little less than 5 minutes. And so the escape velocity is, the surface velocity is 10 times larger than the escape velocity. So there can't be any loose material on the surface. And this is of a size that where we think that clearly some objects have a lot of regolith on the surface, have a lot of loose material, but others clearly cannot. And so if you go to an asteroid of a certain size, you can't be guaranteed that you know what the surface is going to look like unless you know a little more about it. Now, binary systems. One of the big surprises in 2000, I guess, when we looked at DP-107, was that some near-Earth asteroids have satellites. And since then, we've found about 1 in 6 of these near-Earth objects are part of binary systems. And that the characteristics, immediately the idea was, well, near-Earth asteroids, if they come by a planet, they can have a planetary encounter, and that can cause tidal forces to cause them to split. And if it's a rubble pile object, then you can spin off a satellite. Well, that was a nice idea, but it doesn't explain 1 in 6 because there's just not that many planetary encounters. And we also started looking in the main belt at this same size range where the primary is something like 500 meters to 2 kilometers, and the secondaries seem to be about between 20 to 50% of that, typically. And we see the same kinds of binaries out there, and clearly it can't be planetary encounters out there. And so again, by looking at enough of these and looking at the spin characteristics and looking at the size ratios, our ideas of how they must have formed have evolved very rapidly over the last couple of years, as one idea after another turns out to not explain the observations. And we think now that through these radiation forces, the sunlight warms up the surface, but there's a lag so that the maximum thermal radiation of that energy back out is not in the sunward direction. It's slightly off of that. And so you get a net torque from that, and that can spin the object up or down depending on where the rotation pole is pointed. And so over fairly short timescales, you can spin these things up, and if they become rotationally unstable, a satellite can sort of get spun off. And that seems to explain most of the observations, although there are still some peculiarities that are still baffling. Okay, so most of these have mostly spherical primaries that are rotating near their stability limit, around 2.5 to 3 hours. And almost all of them, if you take the angular momentum of the satellite and extrapolate it back into the primary, they're well beyond the stability limit. So the orbital periods are typically near 1 day, although there's a lot of variation about that. And the secondaries are irregular and tend to be slowly rotating. Most of them seem to be synchronously locked, although not all of them. And there's a couple examples where we do have significant eccentricities in the orbits, but most of the orbits are consistent with being circular. The typical diameter ratio is something like between 3 to 1 and 5 to 1. So whatever the cube of that is. And here's another one. This is 2003 YT1. And on this first day, there we go. Now that you're all experts on interpreting radar images, here's the secondary closer to the observer on the first day. And this is nearly a complete rotation of the primary that you're seeing here. And then the next day, it's nearly at the same range as the primary, coming up over here. And we have enough observations to determine the orbit fairly well for this one. And here's another one, 2006 VV2. This one came fairly close to the Earth so that we had to do by static imaging. We transmitted from Arecibo, and we received at both Goldstone and the Green Bank telescope on different days. And well, let me show you another. So here's the movie from the bistatic observations where we have a much longer coherence time. And you can see as you look at the primary, you can see these little bright dots that are rotating around with the primary, and we think those look an awful lot like the boulders that we see on the surface of Eros and on Itokawa. And and this is a remarkably non-spherical primary, actually. So the orbit of the secondary is kind of interesting. That the gravity field may be kind of tricky. Stability zones may be limited. Okay. Early in February this year, we discovered the first near-Earth asteroid triple system, 2001 SN263, and these are observing dates in February down here along the bottom. And here's the primary in the middle, and here's the close secondary, and here's the farther one. Farther one is larger. It's about half the size of the primary, and the closer in one is about a third of that. So it's about a sixth the size of the primary. And so if we just simply assume a circular orbit, it works remarkably well. And the analysis is still continuing on this one, but it looks like a circular orbit is, or very nearly so, is a very good fit to the observations. And the outer one has an orbital period of something like 140 hours, and the inner one is about 16 hours. So the question is, we've seen one triple system out of about 200 binaries are known total. Only 100 or so of those from radar, but from light curve observations we have a bunch more. And so we don't know if this is, if if this is a young system and evolving, there's some people who think that maybe when you spin off a satellite, this is an ongoing process. You keep spinning up the primary, and it gets unstable again, and you just have a whole series of satellites that you just spit out, and then they wander off, and then you spit out another one, maybe. Or possibly these things form if a bunch of material in a landslide type event gets sloughed off at once, it can form two separate satellites, or the interaction of them could put one in an orbit farther out. We don't know. So, in summary, all of the near-Earth objects seem to show just a huge variety of their spin states, of their shapes, of their sizes, of their internal structures. And so if we're going to understand the population, we do need to keep radar observations are one of the best ways to do that, and we hope to be able to continue doing that. Spacecraft images can be more detailed, but to put them into proper context, we do have to understand something about the range of different shapes that are out there, and not just a few detailed objects, and assume those are typical, because it looks like nothing is typical. So let me spend a couple of minutes talking now about comets, because we can also image comets with radar, although it's even less often that a comet comes close enough to get a good image of the type that I've been showing you so far. But we have had a few, and of course we know what comet nuclei look like from a few spacecraft missions, and they also seem to show a great deal of variety, differences from one to the other. And so this is, of course, the nucleus of Comet Halley, seen by the Giotto spacecraft. But a couple of others. Here's Comet Borrelly, seen by Deep Space One, and here's Wild 2 that we're now analyzing the dust from the Stardust mission, and getting a lot of mineralogical surprises from the comet dust as well. And Comet Tempel 1, of course, we actually ran something into it and got a close-up look of the dust that was kicked up off the surface. The Deep Impact spacecraft left a projectile in front of the comet that it then ran over and impacted right about here. And this is a time series showing the bright plume of material that came out, and had a dramatic effect on the composition of the dust and the gas, et cetera. And so we've learned a lot about what the regolith of this object must look like. And the observations before that also showed that different patches of the surface had different appearances and seemed to be heterogeneous. And so comets may have certainly as much or more variety to them than the asteroids do. Now, back a couple of years ago, year and a half ago, I guess, we observed comet Schwarzmann-Bachmann 3, and this was the closest known comet to come, that any known comet was going to come to the Earth for the next 30 years, or the 30 years previous. And so it was a very good radar opportunity. You may remember that this was the comet that was falling to pieces, and had just as many as 20 or 30 identifiable pieces that were visible at any one time. This is a Hubble spacecraft image, HST image of one of the, I think this is of the Nucleus B, and some of the little pieces that were coming off of it. So we detected with radar both the nucleus and the coma of this comet. We imaged fragments B and C. Those were the big ones. C was the main comet, the biggest one. And C had broken off on a previous apparition and was identified returning. But both of them were shedding additional mass throughout the apparition. And we got the first radar image of the coma of fragment B, but when you image a swarm of particles where they're moving through each other, you don't have the constraint that you have a rigid rotator to get your spatial image back anymore. So figuring out what the radar image of a coma means has been a little bit tricky, and we're still in the process of trying to understand that. Now, when you look at a comet, you see not just a return from the solid body down in the center, but you also get a return from the particles in the coma. But the radar, remember the radar wavelength is 12.5 centimeters, and so you're sensitive to particles that are about 2 centimeters and larger. So when we're talking about dust, it's not the same dust that the optical and infrared observers are seeing. That's down in the micron level. Those are completely transparent to the radar. So we have a much clearer view, but we're seeing a different size distribution of the coma than is observed with other techniques. So now, instead of looking at tens of hertz in the frequency range, now we're looking at a couple hundred. But this is Iras-Araki-Alcock from 1983 that also came very close. And so we get a broad echo from the coma particles down here, and we get a very sharp, narrow echo from the nucleus. And this goes up about a factor of up to 100 on this scale, so it goes way off the graph. Oh, I guess it's shown down here. So here's comet SW3 and a similar spectrum from that. Now, instead of the delay and Doppler image, this is if you sum up all the delays just into a spectrum. So here's the coma skirt. You can see it's fairly asymmetric, but you have to take we're only seeing velocities in the line of sight, and so you have to take the comet's geometry into account to see where the particles are actually going. And the return from the from the nucleus is this sharp spike in the center. So if we look at images of the nucleus, this is of the main nucleus, this is C now, on 4 different days in May. You can see the same sort of delay Doppler image here, the observers at the top. And by measuring the extent, this is 1 kilometer here. So we know the nucleus has to be at least that deep. And if this is like we've seen with other kinds of imaging, it's probably closer to 2 kilometers. But it could be a long, skinny thing, and if it's sort of tilted towards you, you may see farther than 1 radius back. So we know it's at least 1 kilometer, probably closer to 2. And we can get the rotation period, at least limits on the rotation period, from the Doppler broadening. And this is consistent with some of the observations from the ground and inconsistent with others. So we're still trying to understand the rotation state of this comet nucleus. And here's what fragment B looked like, at least on one day. So this is a very unusual looking object. And it's unclear from just this one image, is this just a roundish thing that's shedding mass that's coming back here, or is this a very irregular object where it has something that's sticking up that the radar can see that's beyond the terminator? And it may be, those are both likely, and we don't really know from just this one image what's really going on. But it looks unlike most of the asteroids of this size range that we've seen. And here is our image of the coma. I guess it doesn't show up all that well, but it looks like as the particles move, this is velocity and distance again, 500 kilometers now, and as you go farther back from the comet, you see more particles at higher velocity, but right near the comet, you don't see any particles at high velocity, and that seems to indicate that either large chunks are coming off of the coma and then breaking apart and accelerating, or that particles are emitted slowly from the coma and then through outgassing or radiation pressure or whatever are accelerated later. And this is not what's generally assumed when people model the mass outflow of a coma. And in January of this year, we imaged Comet Tuttle, came fairly close, and this doesn't look like any of the other comet nuclei we've seen so far. This looks more like those 2-lobed asteroids, where we see 2 similar-sized lobes that look like they're stuck together, and they do seem to be pasted together in rigid rotation about each other from images on other days. But this is not what we've seen so far with the other comet nuclei that we have gotten a close look at. So it looks like there's at least as much variety among the small icy bodies as there is among the small rocky bodies. And we have a lot more work to do to understand where all these things come from and how they got the way they are. So, future work at Arecibo, there's some question of whether there will be any. We certainly hope there will be. But the funding from the National Science Foundation, which has funded Arecibo for the last 40 years, is somewhat uncertain. The science that is done at Arecibo is divided roughly 75% radio astronomy, and that includes timing of pulsars and that sort of thing. About 5% planetary radar, not just asteroids, but also looking at planetary surfaces and satellites of Jupiter and Saturn's rings and that sort of thing. And 20% is studying the Earth's atmosphere and the upper levels of the ionosphere, and that's funded through a separate agency. Now, both NASA funded the planetary radar up until 2001, and then they stopped funding it and said they thought NSF ought to pick it up. Well, NSF didn't agree with that, and they each think that the other agency ought to fund it, and so far that's where it stands. Starting in April of 2010, the funding for astronomy could decrease by as much as 50%, and there's still some argument about exactly what will happen then. And NAIC, which is the National Astronomy and Ionospheric Center, which is Arecibo Observatory essentially, and Cornell, our managing institution, are seeking partnerships with the universities in Puerto Rico, universities elsewhere in the U.S., and anywhere we can find to try and return to full funding levels. And among those interested are the Spanish Research Council has expressed possible interest in an international partnership with NAIC, particularly with radio astronomy, but it's possible that the planetary science could also be an area where we could both get a lot out of some sort of collaboration or some mutual agreement. So we're hoping that something fruitful comes out of that. So that's, if anyone has any questions, that's the end of my talk.
Ellen, could you go back to the images of the comet that seemed to have shedded, as I think it was Rossmann-Bachmann 3, that had seemed to have shedded a, you might remember that, I'm thinking of the work of Walter Harris with Comet Hyakutake. He found that there were pieces, large chunks that were being ejected along the tail of Hyakutake. That the dynamics would indicate that there were just like very large chunks of the comet that were coming off along the tail. Mm-hmm. Which would be the direction of the tail there?
Well, I don't know off the top of my head, but these are close to the object. Remember, the object is something like 400 meters, and this is a delayed Doppler image, and so that bright bump in the back is within another 200 meters of the primary object. I mean, we're sampling the whole. We're looking through the whole column of material, and in those CW, in those spectra, those are summed up over all of the distances that we see. But this is a regular delay Doppler image that's sampled that way, so we do know the distance behind. Now we have another image of this from 2 days later, I believe, and it looks similar. You see also bright spots in the back, but they're not. Are they the same bright spots, or are they new bright spots? Are they new chunks of material coming off? Either of those could be true.
So this could be topography or
or
chunks that are
mass
coming
shedding, right. Yes.
Ellen, you mentioned one of the binaries you show us.
Uh-huh.
You say that there was also IRTF spectra.
Yes.
Showing the composition of the surface.
Mm-hmm.
From the Arecibo observations, you can derive the densities, right?
Well, no, you can derive a density from, well, okay. You can derive the density from once you know the orbit, and you get some, if you interpret the radar reflectivity in terms of the surface density and the surface porosity, you get a number, but that's the one where you violated all the assumptions that go into that theory. And for a couple of objects, we have both of those. I think Mike Shepard published numbers for CE26, 2001, 2003. I don't remember which one CE26 was. But the density that you get from the radar albedo, which is simply the radar reflectivity compared to its geometric size, you get a density of something like 2.2 or 2.3 grams per cubic centimeter. From the orbit of the secondary, you get a density of the primary that's more like 1.7. So it's much, much less. But you have to remember that the primary source of error in the density of even a binary system, even if you know the orbit and you have projection effects, so the semi-major axis is always a little bit tricky, but even in those cases where we know the orbit well, it's a 30% error in knowing the volume. If you don't have, for the ones that we have the best measured shape for, KW4, where the shape model was just amazingly detailed, if you take the volume that you get from the average radius, or just even the best guess that you could make from the radar extents in the images, you get a number that's 30% too large compared to the actual volume calculated from the shape model, because it's got this elongated ridge around the equator, and it has kind of this spinning top kind of shape, so that the best fit sphere to the radius actually greatly overestimates the volume. So I think when you take that into account, a lot of those estimated densities from the orbits, the binaries, tend to go back up again. So a lot of them look very underdense, and we have, amazingly high porosities, 50%, 70%, that some people think are non-physical. But there's still a very large error in the volume of the asteroid that goes into that.
Well, just a comment about this triple system that you just detected. Those kind of triple systems are very stable from a mathematical point of view. When you have two objects very nearby and the other very far away, they work just like a binary system. And in fact, there are a lot of triple systems of stars, and there are projections that predict something like 5% of stars have triple systems. So I wouldn't bother.
Right, that's certainly true if it was isolated out in space. But remember, these things are planet-crossing asteroids. And their lifetime against disruption from collisions or encounters with planets or other things is only about 10 million years. And so they have a large chance to actually get in encounters and collisions from other bodies that even if they spend a lot of time in the inner solar system, if they go out as far as the main asteroid belt, when they get there, they're moving at fairly low relative velocity compared to the objects in circular orbits. So they essentially sit there still while the other asteroids stream past them. And so their lifetimes against being collisionally disrupted are fairly short.
Yeah, I have a question that is not fully related to your talk, but I would like to have your opinion. Is there any scientific evidence from the dynamical studies of these small objects, particularly those in the Kuiper belt, for the presence of a companion to the Sun, a massive companion to the Sun that is much farther away than 40, 50 astronomical units?
It would have to be much farther away than that. And we can put pretty strict limits on how large of a body could be out there, just because we've now sampled many hundreds of objects in the Kuiper Belt, and if there was something that was perturbing them in a significant way, we would see evidence of it. I think there still could be something reasonably large, much larger than Pluto, out at 100 AU, but there certainly can't be anything at 50 that's of any significant size, or else we would have seen it by now. People are scrutinizing that region pretty carefully. Yeah, there are people who know those limits, but I don't know them off the top of my head. There have been some papers published on that, I think.
Any last question? If not, let's thank the speaker again for this nice talk.
Thank you.